All right. Well, I'm really happy to welcome Tiziana, Professor Tiziana Vistarini from the University of Colorado in Boulder, and an old friend around here to give a talk today on the metaphysics within string physics. So please, take it away.
Thanks for inviting me. Okay, so how should I start? Well, let's start it this way. So it's widely held within the quantum gravity community, into the quantum gravity circle, that string theory is a background dependent theory. This is a quite popular view. And the majority of textbooks and physics textbooks about string theory, and also some philosophical debate, a lot of popular science presentation of the theory, they all share this idea, this assumption that string theory somehow posits some fundamental metric, which is somehow prior, I would say, some kind of metrical background, which is prior to the string dynamics. So, and in other words, they're saying, well, look, the physical content of the theory is not entirely independent on the metrical structure of space-time. So the issue is, well, you know, why we should bother to, make a research or analyze any notion of space-time emergent in string theory, because it doesn't really look like, it looks like a non-starter. The view I'm pursuing here, I'm presenting here, and I have a technical question. Should I look there or should I look where I want?
Whatever feels natural to you.
Okay, if I look there, it's like if I look them in the eyes, right?
Yep.
Okay. Now, now the view I'm trying to pursue here actually argue against this thesis, and this talk is based on chapter 1 and chapter 5 of my book for coming for Routledge, and which will be completely in this time, really in 2 weeks, because my deadline is April 7th. So, and this is a real deadline. So, and Nick knows what I'm talking about. But okay, so I have to remember here. That's okay. Okay, so let's try to say something more. Okay. So let me say something more, still a bit broad. So we do have, so the physical insight about the fundamental nature of space and time are quite, in any approach to quantum gravity, are highly counterintuitive. And string theory, the account of string theory about emergence of space and time is not an exception to that. But in this talk, I want to present two main train of thoughts about the things I've been developing about this notion of space-time emergence. So on one side, I want to read formally space-time emergent into the formal local structure of the moduli space of the theory. I would say something in a bit about what a moduli space is. I don't remember how much familiarity people have with this notion.
You told me. Two Einstein.
Well, so I found out last night it was a bit more, but yeah, no, it was two. Then I had a chat with a friend and said, no, I will put four. Well, okay, that's not important.
I would explain it a little bit.
I can explain a little bit, yeah, I can always say something more. So on one side, and this is what I do in chapter 5, is really trying to derive information from the local structure of the moduli space of the theory, and to show that there is really there are really some interesting theoretical findings that really seems to support this idea of the somehow the blindness of string physics with respect to deformation of the metrical structure. Of course, we do need some constraint in order to support this idea of blindness of the string physics. And the constraint relies on the idea that even if I deform the metrical structure into something which is metrically inequivalent, as long as these two space-time are somehow two diffeomorphic fibers, I mean, somehow argue for my thesis of space-time independence of string theory. But okay, this is one train of thought. The second train of thought is, okay, I want to explain what kind of strategy I'm using here to be able to apply the notion of mechanical explanation to this notion of space-time emergence. And this is not an easy task, for reasons that you will see in a minute, in the next few slides. So, on one side, reading space-time emergence, on the other side, trying to put a label which is that of mechanical explanation of space and time. Of course, in order to do this, since I'm doing something which is not very orthodox, I'm trying to apply mechanical explanation to space and time, and this is somehow seems to be in tension with the traditional school of thought about mechanicism, and as I will show you in a minute. So I will need somehow to present and to try to say something meaningful about the revised form of mechanical explanation that I presented in chapter 1 and chapter 5. Okay, so according to string theory, am I on the right slide? Yes. According to string theory, space and time are emergent feature of the physical world, in the sense that they are mechanical byproduct of more fundamental string dynamics. But let's say a bit more. Okay, so which one here? Okay, I need to do a step back here before going forward, because this step back hopefully would be very useful to understand what is the kind of Weltanschauung which I'm using to argue that there is a mechanistic explanation explaining this emergence. So far, so good? Okay. What I want to say really briefly here, and this is part of the introduction of the book. So, in the philosophy of science fiction, right? And in the philosophy of science literature, sorry, why did I say fiction? I don't know, where it's a kind of Freudian mistake. That's Freudian. In the philosophy of science circle, there is a, I mean, it is, I mean, very widely argued that, well, the macro description of the world, which is delivered by classical, let's say, pre-relativistic physics. So we are really in a classical place. Well, people say, well, this kind of account, without any doubt, they assign to, I mean, it assigns to space and time the status of background features. So they are somehow features which are prior to the mechanical features of the physical world. So they have this kind of stage. Now, my point here is to show, before even moving any further step into the quantum perspective of string theory, to show that this way of interpreting even just the lesson of classical physics is kind of questionable. And I mean, my alternative interpretation, which is the one that I endorse, amounts to trace already in pre-relativistic classical physics some kind of coarse classical counterpart of this notion of space-time emergence, of this idea that space and time are mechanical feature. And even more, I want to say even more. I don't want just to say, look, there is in some sort of, in embryo, some sort of coarse notion of mechanical nature of space-time. But the kind of lesson that we can derive even from a classical Hamiltonian seems to present, seems to show features which are later on developed by the quantum approach of string theory. So there is a kind of nice continuity here that string theory offers in the kind of mechanicistic explanation that it gives about space-time. Now, this is based also on based on chapter 4 of the book, but also there are really two important bibliographic references here that have been, I mean, reading that stuff, I really found a lot of similarities with my approach. One is the most recent book by David Albert, which is After Physics, and in 2015, and the other is Harvey Brown, Physical Relativity, Space-Time Structure from a Dynamical Perspective. These two bibliographic references really, I thought they were really, while I was writing that chapter, I thought they were really matching perfectly with what I was trying to do. Okay. Should I go here? Let's check. All right, so let's do this, and it helps your suggestion because, I mean, I kept reading from in the other way. Thank you so much. I kind of not okay. So let me say something more about this idea that we can extract some lesson about the mechanical nature of space and time, even in an Hamiltonian. And so you do have on my back, this is just a classical Hamiltonian. I'm not specifying here anything we don't really need. It's very basic, and I don't know how many of you are I mean, I know a lot of you have familiarity with what an Hamiltonian is, so, and I guess also the people on the other side. So I'm not specifying anything about the structure of the potential. We don't need to know anything like that. We know it's sufficient to say that the potential, of course, it's structured in such a way that it accommodates, it explains the particle interaction. And so then you can see it from the choice of mathematical formulation that this potential is formally structured in such a way that somehow it is showing the fact that I am positing an Euclidean space as a background. So the idea is just that we have a classical system of n-dimensional particles floating around, let's say in a three-dimensional space, not even consider time for not having complication for now. And this potential is showing the fact that there is a posit here, and the posit is that the actual geometry of the world is Euclidean. So I'm positing this. Now let's pretend, for the sake of simplicity, that we live in a world in which quantum mechanics doesn't exist. So we live let's pretend that we are in a world in which all we need to explain the macroscopic objects like table, chairs, people, cats, and university measuring device, and so on. All we need is just to know, to know this classical dynamics. And so let's pretend we are in a world in which quantum mechanics doesn't exist and there are no quantum behaviors. Now, looking to this Hamiltonian, how would this what are the world appearances? If I read into this Hamiltonian, how would a world like this appear to us? And when I say, okay, I want to specify that here, when I use the word appearances, I'm not referring to any subjective perception of the world around, but appearances here is something that really refer to how the world looks like through the outcome of experiments and the outcome of measurements. So there is no room here for any consideration about my subjective perception. And so this somehow connect also to another chapter, in chapter 4 of my book, and I'm following here a train of thought which is also developed by David Albert, but for reasons in the book I was mentioning, for reasons that are different from my reason. So a physical world like this, the one which is encoded in that Hamiltonian, it's a bit confusing. All right, okay. Would definitely appear like a three-dimensional flat Euclidean world. Okay, but why? Why exactly? Okay, well, let's look to the potential energy. Let's look at the potential energy appearing in the Hamiltonian. And what is the salient feature of this potential energy? Well, I can see that it is, this salient feature is that it's an explicit function of the three-dimensional Euclidean distances. And the potential has an important role in the Hamiltonian because the potential is dictating how particles must interact. So far, so good? Okay. There is a way to say that, and this is something that it will come out when I will be mentioning the Poincaré problem. So somehow we can say that really, if you look to the interaction in the potential, you can see that it is making these Euclidean distances somehow manifest to us. So we understand that we are positing an Euclidean flat geometry of the background as actual geometry, and this information is made, if you like, visible through the formal structure of this potential. So we might say that the potential of this Hamiltonian produces a manifest image of the world. And in this case, we are lucky because just before I said, well, I'm positing that the actual geometry of the world is an Euclidean flat geometry. So in this case, the manifest image of the world, which is produced by this Hamiltonian, is coinciding, is the same as the actual geometry of the world I'm positing. But things are not always so easy, and it's so the next step will be, but what if the relationship between the potential and the manifest image of the world and the potential in the Hamiltonian are a bit more complicated than that? What do I mean with that? Well, what if the manifest geometry does not coincide? It's not the same as the actual geometry. And, well, okay. So you might wonder, okay, what are you thinking about? Well, this was something that traced back to my PhD dissertation, and you guys were there. You know that I've been talking about Poincaré, and that problem has been developed in the book. So there was there is an old story about this mismatch between the manifest geometry of the world and the actual posited geometry of the world. And the Poincaré story about the impossibility to decide by means of empirical data what is the correct geometry of the world, it is a very interesting story, and let me say very few things about this because it is helpful. It is a story. How many of you knows the Poincaré parable of the two-dimensional? Everyone, okay. No? Yeah, well, I can say something more. So basically, it's a story about a two-dimensional world equipped with Euclid.
You said yes, right? Okay, sorry.
Yeah, but I'm going to explain, but just to know whether I should be more brief or more wordy. Okay.
We started at about 1:15, so we have an hour to get
well, I can be wordy. Okay.
No.
Yeah, of course. You know, that's my natural inclination. All right.
By the slide count, we're like a fifth of the way through in a quarter of the time. So.
All right. I'll try to do that. So this story tells about an imaginary world which is two-dimensional, and it is equipped with an Euclidean geometry. So the actual geometry is really Euclidean. But this is a special disk. It's the one that contrives by means of effect of spatial variation of the temperature on the length of measuring rods. So basically, there is a kind of distribution of the temperature, the form of these rods, and so people are completely unaware of this kind of hidden dynamical law, which is extending these rods or contracting the rods. So they are there very patiently, accumulating looking around, making measurement, and making their dynamical generalization out of those measurements. And their dynamical generalization is, oh, cool, we live in a Lobachevsky plan. Okay. let's say that this is a case, we might say that this is a case in which the manifest geometry of the world, the one that arises from measurement and dynamical generalization, does not coincide with the Euclidean geometry, actual geometry of the world. And we can know here, because we are imposing this kind, but the inhabitants cannot possibly know anything about these hidden dynamical laws. Never mind how much carefully they can really make their experimentation. So what this parable suggests is that, well, we may generalize, for example, this parable, let me see, yeah. So, well, we may generalize this kind of parable to the case that we were considering before, to the kind of Hamiltonian in which I was positing as fundamental geometry, the Euclidean one. And let's think now to a background space-time geometry, which is, well, just an arbitrarily curved, kind of arbitrary curved background. And so we know that in this case, the Hamiltonian will depend on generalized coordinates. And if this is the case, in a world like this, space geometry, there is no general unique way of defining the line element ds, right? Because we are in generalized coordinates. So in this case, the potential appear to be a function of this delta s, which is in function of. Oh no, sorry, I forgot. I can't synchronize myself with it because it's not my computer. Sorry. So yeah, maybe I could sometimes you can see. So we have the now it is a function, so it's pretty much the same, but you can see the difference there because we are now it's representing the functional dependence on the coordinates of u in a different form because now we are on an arbitrary curved manifold. Okay, let's check now. Okay. Oh, yeah. So, so more generally, that means that really interaction between particles can be seen as, in this case, manifesting. So the interaction, I'm saying the interaction because I'm talking about the potential, okay? So the interaction of particles are manifesting in a Euclidean flat space geometry. And so the situation is that this world in which we are now living, in spite of the fact that it is actually curved, it appears to us, who are the inhabitants, as a Euclidean flat space. So at some point you may wonder, okay, but in this scenario, the Poincaré scenario, what does it mean to say that the space is actually curved? It seems like the actual curved geometry of the background here does not have any role in producing the manifest image of the world. What is doing the job of manifesting in producing a manifest image of the world is actually the Hamiltonian. It seems that the work is all on the dynamics here. So, and this is completely independent on the fact that we were positing that there is a curved space-time, a curved background. So the idea is, okay, can we make a step farther here? Can we say that, after all, it seems quite simple to see that this Hamiltonian, this potential, is producing a manifest geometry, whether or not there is a fundamental geometry postulated in the background. Because I can't really see, and this was somehow the kind of lesson that I extrapolated from Poincaré, right? I cannot really see what's the causal role, what's the explanatory role is played by this posited actual geometry. So maybe it seems kind of legitimate to think that if the work is all on the dynamical laws, so then they produce this manifest geometry whether or not there is a fundamental metric. So, and you can see here that we can somehow extrapolate from the classical Hamiltonians. I'm not even mentioning the word string or quantum mechanics. I'm not really saying anything about quantum. There is already there, somehow in an embryo form, in some sort of coarse way, and a kind of lesson that tells, look, space-time geometry may not really seem having anything to do with the actual background structure of our world. It seems more like it is a kind of mechanical, emergent thing, a kind of mechanical product, like, I don't know, as I would say, table, chairs, people, and cats are mechanical byproduct of dynamical laws. The underlying structure may be not geometrical at all. And maybe, and this is what I'm adding here in order then to extrapolate this course lesson and to create a bridge with string theory, maybe all we need here to say about the fundamental structure of our physical world is just say, look, we only need a topological structure. Topological doesn't imply necessarily metrical structure. Topological is just something weaker than a metrical structure. It is something stronger than just a set of points. So we can maybe weakening our condition. And now you can see that the line of reasoning that I'm following here in this classical case can really be generalized to a quantum perspective, and the point is that in the classical physics, in the classical pre-relativistic physics, one school of thought against the other, it seems really that they don't really make a huge difference in deciding which one is the correct one. So whether my reading, or it's not just a lot of people out there are reading the classical Hamiltonian like this, and as opposed to the people who are thinking that there is a fundamental matrix. But when we move to the quantum perspective, the manifest image of the world and the actual structure of the fundamental structure of the world, they fall apart. And that is why we have to deal with a lot of difficulties. And that is why what? Sorry. Yes. Yes, this is exactly. I always anticipate my slides. I'm sorry. Yeah, no, it's so. Okay. Okay. Now, let me see. Yeah, I mean, just want to make sure that, yeah, I think I skipped, but that's okay. So, so in the quantum gravity description, the moral of the story, this is still the old one, right? Assume underlying fundamental structure, yes, sorry. This is the first time I speak on YouTube in this way, so I get confused with this. I keep pushing the wrong one. So in the quantum gravity description delivered by string theory, the manifest, I already said that. Now, I want to make a reference here to an important book, and a wonderful book that I suggest to read. It's really great. It's a kind of summary of all the things that David has been doing in the last years. So he is developing a similar train of thoughts, heading to this idea that space-time is not fundamental. I mean that there is a known space-time fundamental arena in which the quantum dynamics unfold. And this is, he's doing something slightly different. He's thinking to foundation of quantum mechanics, and in his case, of course, if my reading is correct, so he is he's speaking about this fundamental arena, okay, this fundamental topological arena, differentiable arena, which is not metrical, is basically the space of configuration of the universal wave function. And I read some of the chapters of his book, and if my reading is correct, the space of configuration in this scenario, in the scenario of David Albert, is actually the totality of all possible values taken by the universal wave function at any particular time. This is the kind of scenario that he delivers. This manifold is not geometrical at all. It is a topological manifold, and the manifest geometrical image of the world, the one which we are familiar with, would emerge, in his account, somehow from this configuration space by means of the work made by the quantum mechanical Hamiltonian. So you can see this is a kind of different context. So I'm going to use a space of possibility as well, connected to the string theory approach, but at this point our paths become different. But this is the kind of Weltanschauung that we both share in this attempt. I wanted to say before, I was mentioning Poincaré, right? And I don't want to give you the idea that here I'm just extrapolating Poincaré from the context of the historical debate they had back then into my context. This was a mistake that I did in my PhD dissertation. But I was young back then. So what I'm doing now is actually, of course, everyone knows that the Poincaré debate, right? It was more about the epistemology of geometry. So, the problem is we can't really individuate the correct geometry of the world by means of empirical data. There is a problem of underdetermination. But here, my use of this lesson is somehow at the right angle with what Poincaré was doing, because he was inquiring about the epistemology of geometry, and I'm trying to derive a lesson about physics, and I'm trying to use this problem of underdetermination of geometry by physical data to try to give a sense in which we can make intelligible, to speak about the mechanical explanation of space and time. Okay, so as I said, my thesis, so I do have 50 minutes, right? 45 minutes, 1 hour.
About another half an hour.
Half an hour, okay.
From now.
From now, okay. I am Italian, so 40 minutes, because Italians are never precise.
20 minutes.
No, it's just a matter of smooth deformation. We can delay time, and you have been in Italy, right? Everyone was showing up late, so okay. My thesis, as I said before, because I wanted, it formulates it basically it's in 2 points. So. First, the idea that string theory physical content is independent from space-time structure, and this is based on the formal reading, on my reading of the formal information in the local structure of moduli space. And this is a train of thought which will be heading us to the underdetermination problem. So I'm rereading the underdetermination problem into the local structure of the moduli space. And the lesson about metaphysics I get here is that string theory does not really posit any fundamental geometry. Rather, what the kind of information that I am gaining from the local structure of the moduli space is that it might posit some fundamental topological non-metrical structure, which is much weaker than the metrical one. But this is something that we will unpack a bit better. Okay. Second, based on all this, I try to say something, as I said, as much meaningful as possible of how space and time can be thought in terms of mechanical byproduct. And this is really a way I'm trying to extend the definition of what the traditional definition of what a mechanical explanation is. And basically the bridge between these 2 points will be, roughly speaking, I had to be very concise in this slide, but this is very well explained in the chapter, is this underdetermination problem. Okay, let's go here. Now, what, yeah, sorry. Yeah. Blah, okay. Are you guys having problem with they will say something, right? If they have a problem with phone. But Chris left, so he must be very angry about the mess I'm doing with this.
I don't know where.
Oh no. No, please don't go.
You just go on the computer that's in the corner.
I thought it was just, it's enough.
You guys okay?
You guys okay?
Yeah, nobody's leaving. Everything all right?
Okay. I'm not messing everything up here
Okay.
because I'm making mistakes with the slides.
You continue. It's all right.
Go on.
Okay. Okay, but why did I use in the slides before the word and now afraid to come back? Yeah, well, some intelligible, I mean, as much as I can, because look, one of the challenge of the book here is to say, well, so you could say, okay, you want to give me this idea that in string theory there is a mechanical explanation. I mean, the space and time are treated as a mechanical byproducts and produced by underlying string dynamics. And yeah, okay, that's very nice. But how does it work really? Because here the huge problem we have is that is connected. I mean, just think to the kind of historical use of the term mechanical explanation, right? So there is huge centuries of history of philosophy, and it is quite evident that in the past and in the present, the vocabulary in which am I on the right? Yes. The vocabulary in which a mechanical explanation have been usually formulated presuppose at least time as fundamental entity, if not, and sometimes also time directness on the top of that. So, and this point, note that this point is not merely linguistic. In this sense I'm speaking, this is really a huge challenge. It's not merely linguistic, because it indeed reveals the substantive role which is played by the notion of initial condition in what a mechanical explanation is. And any historical attempt of mechanically explaining phenomena use somehow, I mean, they all share this idea of initial condition of a system, right? And it can be, of course, if you don't put on the top of your framework any time arrow, you might say, well, an initial condition, initial doesn't mean necessarily in the past. An initial condition can be in the past or in the future if you are dealing with a time irreversible laws. And you can get rid, you say, oh, I don't think there is any time arrow out there. It's not any metaphysical, there is no any metaphysical fundamental time arrow, but still you have to deal with the fact that initial condition of state of the system which are in some time and in some space. And so how this can possibly work? An initial condition, of course, once arbitrary fixed, crucially account for the system behavior, of course, in combination with the dynamics. Yeah. Back? Oh, no, yeah, sorry. Oh, no. What am I doing? It's not working. I'm in panic now. Okay.
Tell you what, I'll do it here.
Yeah. No, it's okay.
I'll do it here as well. The keyboard goes to sleep if you don't sort of press the button for a bit.
Sleep? No, did you say, sorry?
Yeah, the keyboard, I mean, it's...
Oh, the keyboard.
So my keyboard will go
no,
to sleep.
I thought the people are going to sleep.
No,
I understand. Okay. So we are trying to sleep here.
No,
okay.
So sometimes you have to press it twice.
No, okay, keyboard, sorry. So any initial condition of the system is, as I said, once arbitrary fixed, crucially account for the system behavior. And of course, the traditional mechanical explanatory role of an initial condition is in virtue of being a physical state in time and in space. Okay, which is, in other words, well, look, the explanans and the explanandum, normally they live in the same physical space-time. After all, this is the great legacy of modern scientific revolution, right? I mean, historically, the mechanical explanation was proposed as opposed to the teleological one, which, according to which explanation of phenomena may also reside outside the res extensa. So when I claim, and by claiming, and any other out there claim, that space and time are emergent because they are susceptible of mechanical explanation, I'm also simultaneously extracting them from the set of constitutive features of the mechanical explanation. That's a kind of big problem. So, and it is really hard to imagine what is left of a mechanical explanation if space and time are removed by this list of constitutive elements. So the worry might be, well, here the risk of an unintentional restoring, some new update, well-dressed teleological version of what counts as a scientific explanation of phenomena is really palpable. So what I do was, well, look, to bypass this difficulty, I had to rethink a way to revise the traditional notion of mechanical explanation, to say, look, mechanical explanation does not really require any posit about the existence of a fundamental geometry. Maybe it only requires some fundamental topological, non-metrical structure. When I say, I mean, you know that not necessarily a topology has a metrical structure. I mean, you can have metrics induced by topology, but you can have topology which are not susceptible to induce a metrical structure. All right. Okay. All right. So now, okay. And so this was just to let you know, before starting, what are the main obstacles on. I'm sorry. Yeah. Did I say something weird?
Oh,
No.
just we have about 20 minutes.
Oh, okay. Oh, well, this is something just, well, this is the kind of, I wanted to give a broad context. Otherwise, I didn't want to speak about moduli space. So what does it mean to familiarize? So this is the first block, right? The first aim. Familiarizing with moduli space. Well, I said, well, I claim that I can read back space-time independence on the local structure of the moduli space. But what are these moduli space? Well, we are thinking to the moduli space of string theory, and the way in which I'm using moduli space is not even sticking faithfully to the most contemporary way of using it in physics, which doesn't take too much in consideration the very nice formal structure. So it's something that includes any kind of duality. So I'm not focused on T-duality or holographic duality and so on. And I'm especially emphasizing the topological structure, which I think didn't get the attention it deserves. This space didn't get the attention it deserves. It is usually a kind of useful framework to show how duality works, but there is much more written there. So these are spaces of parameters, and what does it mean to say, well, you can simply have a space which is not a physical space, but it can parameterize physical space-times. Of course, moduli space comes from algebraic geometry, and they can parameterize whatever you want, any kind of object. But we will be focused here only on the fact that they parameterize physical space-time. And when I mean physical space-time, physical metrical structure. Okay, what does it mean to say that we have a space of parameters? Well, M, let's call it M, is a space of parameter for some family of kappa of physical spacetimes, only if, and this is really a necessary condition, that's why I say only if, it's not sufficient, if the correspondence between points of M, okay, and physical spacetimes with diametrical structure is 1-to-1. So the relation is that the physical spacetime is in correspondence with a point of this moduli space, of this parameter space. Every time you change the metric here and you pick another spacetime of the family, you will end up with finding another point in the moduli space. Now I want to give you an informal definition of what a sufficient condition could be to be a good moduli space. It's, well, look, if I take two space-time here in the, let's call it two space-time with diametrical structure, and they are very close. What I mean with close? Well, close with respect to the fact that they are a very infinitesimal deformation of each other, and so they are close with respect to the topology of the set which is classifying them. Well, I must get something. I must get 2 points in the moduli space which are close as well with respect to a different topology, because in principle the topology of the set of space-times is not the same of the topology of the moduli space parameterizing them. So, and that is a good thing, because you might have moduli spaces that do not have their own space structure, and they are not very useful, usually. You want to build moduli space having their own topology, okay? And whose point are connected by their own topology, which in principle is not the same as the one in space-time. Okay, so what we are going to do is not just having its own topology, but we are going to posit, to put on the top of that topology a dynamical structure, which will be absolutely important to show in what sense I mean that that string theory physical content does not posit any fundamental metric. So okay. Now, okay, you have to know that now at this point. No, this was the one I was reading, right? Mm-hmm. And now, since I couldn't use LaTeX, I have to paste and copy one page of. I mean, I'm taking this picture from the book, okay? So I'm not. This is me, and so sometimes you read it. I mean, I know that you don't have to read this slide right now. Just listen to me, and I'm going to. What does it mean? This is the section on space-time metaphysics within string physics. Unfortunately, I didn't find any fast way to, because my LaTeX wasn't working in the PowerPoint. So, and I have some formula to show you. Sorry, let me do this. Okay. So, so this is the point. How this is going to work? Well, let's say that here you will read words like section, chapters, but just ignore them. Let's try to stick to a representation of the stringy space-time. What do I mean here? Well, we need to say something that I forgot to say before, but it works quite well if I say now. Space-time requires, as everyone knows, extra dimensions, and usually the way in which mathematically they are indicated is, can I move myself? Yeah, okay. It's this one. So you do have, well, I know, I feel like it's very, very small here, but you can see that here we have S times. Okay, no chunk. Oh, it's, yeah. So this, yeah, I mean, you have S times K.
And if you need to point to things, there's a nice ruler over there. Sorry, I should have put it out. There's a yellow ruler in the corner.
Here? Or?
In the corner of the room. Yellow ruler.
Oh.
If you want to point. But I think you should write, because nobody can see that. Yeah.
Yeah. But it's, I thought everything compacted can be read easily, right? No, okay. I was wrong, sorry. S times K.
Do it over there. Yeah, the chalk is better, okay. I think.
Okay, so this is the kind of very basic sketch in which, I mean, they are represented as a product space between a ordinary four-dimensional space-time, usually picked from the class of solution of general relativity, to which sorry, compact extra dimensions are attached. Sorry, and we do know that the theory requires extra dimensions for consistency reasons. Also, extra dimensions have somehow a very important role in producing the standard model of particles out of string theory at low energy. But let's say that I want you to say, well, I don't want you to think that you shouldn't think to this positing, to this postulation of extra dimension as something which is in tension with this idea of showing that space and time are mechanical byproduct. Because although the methodology in a lot of books just presented this extra dimension like something which is posited, extra dimension are a dynamical feature of the theory, and they are somehow really a mechanical byproduct of string dynamics. And there is a sense in which, if you happen, there is a way in which we can say that one of the ways in which string theory makes contact with low energy physics, and especially with some version of the standard model of particles, is really arises from the way in which open strings connect to these extra dimensions, and the topology of this extra dimension is what it is absolutely crucial to produce the dynamical laws that underline the phenomena. So somehow, when we think about extra dimension, it's a topological claim, and in this case, this topological claim is a claim about the law. It's something which is intrinsically dynamic. So, and I think that somehow even this extra dimension, they are playing a role of dynamical entity rather than fixed background prior to the string dynamics. Okay, so they are byproduct of string dynamics. Okay, it's so small I cannot even read, so I got punished by my solution. But so what we are going to do is, okay, how do you build the local structure of the moduli space? Deformation theory. Why deformation theory? Well, because the deformation theory technique, not the whole branch of deformation theory, but some tools of deformation theory give us the chance to build locally this moduli space by gluing together different deformation of space-time metrics. And deformation theory, it really does this role very nicely. This, of course, creates the idea that the moduli space is a differentiable space, is a topological structure, a differentiable structure as well. And also on the top of this topology, we are going to put some dynamical structure. And of course, I want you to keep in mind that here we are, I don't want to create confusion here. So when I say that there is a differentiable structure over the moduli space that arises for reason that you will see, if I am, in a second. So the differentiable structure of the moduli space does not belong to the same category of the differentiable structure of a space-time, because the relation is like one to the whole. So a single space-time it will be a point in the whole. So technically speaking, the differentiable structure of the moduli space arises from the C infinite smooth deformation you do among fibers. So it belongs to a different category. And whereas we have a traditional notion of differentiable manifold on the other side, which somehow got encoded in that. Okay. So that means, well, smoothly deforming compact manifolds, and so what we are going to deform are exactly this compact manifold that we attach to the ordinary four-dimensional space-time picked from the Einstein field equation solution. And this is not surprising, the fact that people keep constantly talking about this compact dimension, because, as I said, really a claim about their topology is a claim about a law. So And so deforming them is absolutely crucial. And you can see you can deform them in such a huge variety of ways. Some of them, are also called the Calabi-Yau manifold. And you can see that there are so many. Here the underdetermination problem arises because you have so many different Calabi-Yau manifolds that can be compatible with the production at low energy of the same ordinary phenomena. But well, you see how you formally do this. Well, what we have is just to build a family. Well, what I did was to build a family of a differentiable family of manifold K lambda. How do you do this? Well, it's not very difficult. You take a set of parameters. Well, these parameters can be, let's think for sake of simplicity, a disk in C, the complex number. So a subset of the complex number. Then you can come up, and this is taken from Kodaira Spencer, famous book, Complex Manifold and Deformation of Complex Manifolds. I don't have the book here with me, but it will be in the bibliography. What you do is to come up with a function that connects a parameter to a compact manifold. But what does it mean? How does it work? Well, it doesn't work very differently from any other ordinary function. The only difference here is that, so this map is a function defined of a set of variable parameters. It takes some value on a fixed parameter lambda and some other value on a different fixed parameter lambda. And remember, the parameter are points in a moduli space, and each value taken by the function is a complex compact manifold. So you have a function that takes a parameter and map that parameter in a complex compact manifold, K lambda, I call it here, K lambda. Unlike a genuine function, here you have that there isn't a unique space containing the whole range of functions values, because each value is a compact manifold, so there isn't something that unifies all of them. So so this is the way this junction here that you can see is a way of representing a bigger object, which is equal to the union of all the values taken by this function, then map lambda from a set of parameters to a compact manifold. And well, this is a numerical domain containing C. Now, the choice of having here a one-dimensional space of parameter is just for the sake of simplicity. Okay, so of course, we will be better off if you want to gain a differentiable structure.
5 minutes.
No, come on, 10. If we want to see,
I don't think you have time to go through in detail everything that's in these.
Well, the
slides.
idea.
Is it possible to?
Okay.
Sort of summarize a bit
Yeah. Let's skip. So you want to. So
then,
you can.
Then we might have 10 like this.
Okay. Thank you. The dependence of this function cannot be. It would be better if this function that map lambda into the manifold is a C infinite function. This is because you want to get a differentiable structure over the moduli space. And but we want even more than that. We want that this family is actually, well, at this point I want to show you the condition to have a differentiable manifold of, well, not here, but they will be uploaded, right, somehow. So, okay. So what we want is not just a differentiable manifold of family of manifold, but also a differentiable family of deformation of a central fiber of the final manifold. Okay, and so how to deform a complex manifold? Well, the way of deforming a complex manifold, and now let's see. So what you are doing is simply basically, I have to skip a lot of things here. So deforming the gluing function. So what does it mean? Well, imagine that you have a compact complex manifold. A complex manifold which is not compact is simply a manifold which is covered by an atlas of charts, and each chart can be seen as something immersed in CN, let's say. in the linear space Cn, but you don't have to. But that's a way of representing. Then if you want a compact manifold, you need to, that means that you have a finite number of this chart. Now, of course, these charts are there. They are creating your compact manifold, but they are all here, and there are transition function in the differentiable analysis that brings point and that change coordinates, and there are also gluing function of all these patches. So I'll be very fast, okay, on this. So if you deform this gluing function of the manifold, you get out of, I mean, the result will be a manifold which looks like the original one, but it is different because you are basically deforming the gluing function of all these patches together. So let's say that it's like you have an object, you break the object, and then you put the pieces together, and if you can put the pieces together in a way which is faithful to the original disposition, but you can still keep gluing together all these pieces in way which are slightly different from the original disposition, and that will produce a different object. So this means deforming gluing function. I don't know if this simple metaphor helps. Okay. All right. So you see the F, E, K are simply the gluing function that depends on the coordinates of the point of the manifold and from the parameter lambda. So the parameter lambda is, remember, the parameter which is moving, which lets you move on the moduli space, because as soon as you change lambda, you are transiting into a different metrical structure. Okay? And now there is an important thing here. So we don't just want, as I said, differentiable family of manifold. No, much more. Differentiable family of deformations of manifold. No, even better. Differentiable family of first order infinitesimal deformation. Why? Because these are the guys who are giving us the information we need. And you can see now the transition, the gluing function here, which are listed in phi 1 and phi 2, have a dependence not only on the coordinate zk of the point of the manifold, but also on the parameter of the family. Now, what we want to do is taking a derivative in lambda on both sides of phi 1 here. The phi 1 is there. You see, this is readable, right? And so we take the derivative, because why are we taking this derivative? Well, what we want is to gain information about what happens to some chosen metrical structure if it is infinitesimally deformed. Here I skip something very important. So if you so we are not deforming the differentiable structure. All these fibers in the family, they all share the same differentiable structure. Why? Because I'm deforming by using a C infinite smooth deformation. But they are metrically inequivalent. Why? Because I'm deforming their complex structure. And complex structure comes with an Hermitian metric. Well, there are things that we should say about this, but I mean, I have to skip this, and we can leave this for the discussion. So the goal is really to show what happened. I mean, when some chosen metrical structure is infinitesimally deformed. So the derivative of the gluing function above gives the rate of their change with respect to the parameter lambda of the family. In this sense, the derivative gives information on all the direction along which the original metrical structure may bend, if deformed. And so each bending yields a metrical structure slightly different from the original. So this is the story I was telling you before, right? So you can break an object and recompose all the pieces together. But why do we need to understand this? Well, look, the important rationale behind this need of clarity, because we really need to express clearly all these bending activities. So we do need a mathematical language that expresses what's going on when I'm bending a metrical structure. Why is that? Because we need clarity. This need of clarity is dictated by the need of understanding what happens to physical observable of any string system if we change the space-time provisionally posited. Okay? So if you change lambda, if you start to take your walk over the moduli space and you have your quantum systems, okay, and you move from one lambda to the other, which means you are bending your manifold and you are ending up in another metrical structure. What happened to the observables of your quantum system? Because if you can show that there is a preservation of the physical property of the system, then you are saying, look, as long as I take in consideration diffeomorphic fibers of the family, diffeomorphic deformation, metrically inequivalent, we can say that there is an independence of the physical content of the theory. And what does it say that? Well, it says that for the way in which this tells to me that there is no dependence on positing, there is no posit of fundamental metric. There might be posit on some existent differentiable no-metrical structure. I'm using coordinates here, and some of you probably is thinking, hey, you are using coordinates here. But look, coordinates do not necessarily involve a matrix. I mean, you can introduce...
We're out of time, by the way.
All right.
So really,
okay.
2 minutes. And then really we should stop now, but...
No, really, all right, okay, I will stop. Well, let me see. So,
No, there's no time, really, we want some questions. I mean, unless there's something really crucial.
No, well, the only crucial thing
we
was...
can talk, the people that are here can talk about this later on, but these
Can
guys
they,
have
the
to go
people,
to...
because I know that people want to ask questions, they can ask questions?
Yeah.
Okay.
Do you want to sort of...
Well, the idea was
So
once you have this kind of topological structure that shows you that you can, so you have to put a fiber bundle over this topology. The fiber bundle is made of fibers which contain the quantum system and it's observable over a certain space-time. Let's call it lambda 1. Then I show you that exists a way to, of course, I mean, this is not my theorem, but there is a way to transport, to make a parallel transport of information along the moduli space. And you can find that there is a way to map the same quantum system over space-time lambda 1 along a certain path, which is the one given by the parallel transport, and which is the one that comes out of this equation, this one. There is a unique solution, which is such that once you bring this fiber over lambda 1 over the fiber over lambda 2, there is a linear isomorphism between the two, and so the physical properties are respected, although the metrical underlying properties are different because they are the result of deforming one from the other. And yeah, you want me to stop now, so I'm now compelled to stop.
And but this brings back to background independence, right?
This brings back to
space.
to the fact to the posit. This brings back to the fact that it doesn't posit a fundamental metric. It might points to some weaker structure in which maybe string dynamics unfold, but definitely non-metrical structure. And also, it shows what does it mean to read the underdetermination problem here. The same underdetermination problem I was reading in the classical Hamiltonian. So there is really no, I mean, it seems like the dynamics are really producing the manifest image of the world because they are preserved even if I deform this space-time metric. So more space-time metrics are compatible with the kind of physical properties and physical dynamics of of the system. And so somehow we might say that geometry is undermined by physics in this new language of moduli space, which is just a more formal dressed, better dressed formulation of Poincaré undetermination problem. And in the same way in which before with classical pre-relativistic Hamiltonian I was deducing that because the dynamics are doing all the work producing the manifest image of the world, whether or not there is a fundamental geometry, now this is applicable. I mean, and this is what brings me to say that space and time are mechanical byproduct of dynamics rather than prior feature and existing prior to the dynamics, to the string dynamics. In the same way, I can just formulate this in the moduli space language to say, look, we do have here also an underdetermination problem arising from this more formal structure, and we can give the same kind of solution I gave before in the case of classical pre-relativistic Hamiltonian. So the fact that a fundamental geometry doesn't have any causal explanatory role in the manifest image of the world, and this comes out in a kind of neat, complete, formal, sophisticated picture delivered by the moduli space of the theory. So.
Cool. Thank you very much.
Yeah, you're welcome.
Okay. Do you have some questions from Geneva? We usually start that way. So, Chris.
Do you hear me?
Yes.
Okay. I haven't followed all of how that's supposed to work, but I'm trying to understand the main claim here. So we're starting out from some product of general relativistic space-time, four-dimensional general relativistic space-time with some other space K, in which you have some dynamics encoded, and that, well, you know, the structure of that K is then that which gives rise to the stuff and its dynamics in S somehow.
Yeah.
But the claim seems to be going further. You say that no, it's not just stuff in space and time that comes out of K and its structure, but it's space and time itself. So somehow the S there is not space time.
Did I say that? Sorry. So you're saying that I said that somehow the S is not space-time there?
You say that space and time are not fundamentally built in, they're mechanically somehow emerging from the dynamics in the K space. So why is not S already space time?
S is not prior to the string dynamics. When I said S is picked from the class of general relativity solution, I'm also referring to something which I've been actually writing with Nick, deriving general relativity from string theory. So I just wasn't focused on S in that case because we were talking about building the moduli space, and moduli space has a lot to do with the deformation of the compact extra dimensions in string theory. But S is, there is a quite interesting derivation on which we have been writing a paper that shows that the metrical structure of the solution to the Einstein field equation are basically derived from the quantum dynamics of string. It was just not the topic of this talk, because this talk wanted to heading to the important property of moduli, local structure of moduli space. So I have to shift a bit the perspective here. So if you are focused on S, well, the situation is even better. It's even less ambiguous, because on one side there is a formal derivation of the Einstein field equation from the quantum string action, that it is a consequence of reimposing conformal invariance. You know, we have been discussing about this, right, in the past. So you quantize the classical string action, you lose conformal Weil invariance, then you need to reimpose Weil invariance on the quantum string action, and in order to control some bad behaviors. And then from this constraint, we can, by taking the low energy, we gain the solution of the Einstein field equation. And this is a kind of a very neat derivation, which was presented by Witten in the early 90s. But this derivation comes with another insight, historical findings about string theory by Sass again. So the fact that the spectrum of the strings modes of vibration produce graviton. So we have these two components in order to try to build a theory of background independence with respect to the general relativity structure. Well, the geometry is in the theory. The geometry is produced by quantum string theory, insofar as strings vibration produce gravitons in a certain level of the spectrum of the string vibration. But it's not just that. They produce graviton, but they also impose how they must collectively behave when they are in a coherent superposition. And the way in which they must collectively behave is according to the Einstein field equation. So somehow I wasn't really focused on saying anything on S, because that would have opened a chapter that would have brought me far from these techniques that I want to use.
Chris, I can see Chris has a follow-up behind you.
Yeah, sorry.
Yeah, go ahead.
Yeah, sorry. Very quickly then, it sounds to me a little bit as if in string theory we get general relativistic spacetimes twice over. One time from the sort of more sorry?
Yeah, no,
yes. So what?
Say it again.
One time from the relativistic space-time S or the symmetry properties of that, where you can see that the first order you get Einstein's the Einstein-Hilbert action from that, and moreover the moduli spaces and the quantum states there, which give rise to gravitons, which are somehow the mechanical the fundamental mechanical devices that give rise to that geometry.
Yes.
Is that correct?
Yes, this is correct. And this kind of space-time emergence, which I call general relativistic space-time emergence, does not rely on the notion of string dualities. Do you agree with me? And so it's a kind of chapter separated by, why not? Well, because you get out general relativistic space-time out of string theory, you have to take, not you work with the string action for a while, then you have to take the low energy limit, and that is telling you, look, there is no duality here involved, okay, because we have that. I mean, I would say that this low energy limit is the physical counterpart of what you would say, well, in some sort of a metaphysical notion of asymmetry between what you derive and what it is producing, that derived object. So what I'm saying is that yes, you are right, that is an emergent product as well, but it is an emergent product as well of string dynamics, which has a methodology which is which can be explained by using a methodology which is not that of the dualities language, and the moduli space is a generalization of the duality language. And it explains, for example, the kind of blindness to metric which, for example, T-duality shows, or mirror symmetry shows, or other kind of dualities involved in the string theory world, let's say. But yeah, no, I do agree with you, of course. There is nothing given for granted here. There is no metric posited, not even S is posited. It's just that it was not part of the talk, but it is in chapter 3. 2, sorry.
I have a sort of finger-like follow-up question, because I was a bit surprised by what you just...
Chris?
No, I do.
Oh,
what
okay.
you just said to Chris, because I heard him ask you whether the story you gave about gravitons was relevant to the moduli space story, and then I heard you say yes, but I didn't think that was the right...
it is... No, okay, no, let's...
I think I understand Chris's question.
Yeah,
the story you were telling, just focus on the story you were telling today, which refers to the compact dimensions.
Because
does that actually give you a route to the Einstein field equations and general relativity?
It gives a route to
another route?
No, it gives a route to the compact extra dimension string theory, the topological structure of this of this structure, their topological structure crucially contributes to the production of the standard model of particles in S at low energy, because that topology is crucial in the way in which then also you have to take in consideration how the strings attach to this extra dimension, how they vibrate, and so on. So what I said about S is that of course there is a connect.
Going back to K.
Okay.
So I think you can nod, Chris. I thought that was what you were asking. But so he knows about. So there's the first route to general relativity through the Weyl anomaly and the Einstein field equation.
Yes.
I thought he was asking whether the story you were giving today was a second route to general relativity, or whether something else was happening.
It's a more radical. I would say it's a second route to a claim of independence from metric, because only showing that you can derive general relativistic space-time out of the quantum string of the action is not enough to claim a strong thesis of background independence. And when I say strong thesis of background independence, I mean independence from any kind of metric. In that case, you might say, look, there is an independence with respect to the solution of the general relativity equations. But I wanted to push myself even further than that. I wanted to say, look, there is no whatsoever fundamental metric posited there. And it's not just a matter of, well, there is some metric posited because that maybe do not belong to that class of solution. But the idea is not even any kind of metrical deformation. I don't know. Am I being very confusing? No.
I think that.
Sorry, because I cannot see you.
Did that sort of address your question, Chris? I guess I want to ask some questions here.
Something happened to
that was what you were asking, right?
Something happened to the audio.
Yeah, no,
I saw.
let's come about it. Yeah. I'm going to ask some questions here then. I think that I saw Chris nodding, so I'll come back to you guys in a
Chris,
in a
did
minute.
I answer your question?
Yes.
Sure.
Okay, questions from here. Keizo.
Oh, sorry.
Yes, so I was thinking a little bit about. I think I'm generally positive to this idea of explaining how string theory could be background independent.
You said
I'm
opposed?
positive. No, I'm not
Oh, positive.
to-
Oh, no, I
think
thought
that's
you said
correct. I
opposed.
think I basically agree with you, even though I don't follow all the details. But what I would like to say, so it's basically, the thing is basically roughly like this. You fix a point in the modular space. For each point in the modular space, that corresponds to a specific space-time compactification.
Yes.
And when you move in the modular space a little bit, that corresponds to deforming the picture a little bit. So, and what you said there about that being close on the modular space topologically means that the metrics on the kind of on the space-times that those points correspond to would be close as well.
Yeah, there is a smooth infinitesimal deformation.
So,
yeah.
so you have these deformations. But what I was slightly confused about was, because you said,
Yeah.
okay, now we can deform the metric. So we haven't really fixed the metric. But then you kind of said we still might have some kind of topology that is fixed. Do you then mean the topology of the specific deformed manifold? Because
Oh
then-
no! I mean, what I mean is, I know what you mean. So what I mean is, This is a good question. What I mean is that, okay, let me paraphrase my statement. Maybe this is more clear. So, as long as you deform the metric in a way that you get out of your original fiber other fibers which are diffeomorphic to the original one, then you have this insensitivity of string physics to metric. So in this sense, they share the same differentiable structure. All these fiber. This is a differentiable family. And this tells something about string theory physical content. It tells that it's not positing a fundamental metric as long as you are walking on your moduli space in the area in which the other fiber are diffeomorphic. So maybe what it is posited by string theory is something much more weak than a metric, just a differentiable
Yes,
structure.
but still, what I'm saying is that that seems to be, you want to go even further than that, because we have all these different compactifications. They don't even agree in terms of diffeomorphic structure.
It's true.
Because they could be topologically different.
They can be topologically different, yes.
For that reason, and it's also a little bit says, even though, because when I'm thinking about dualities, you have two moduli space. You have one moduli space for one type of compactification, and you have another moduli space for another type of compactification.
Exactly.
And then you identify over these things.
Yeah, because they produce the same phenomena,
Because
low
they
energy
produce the same
phenomena.
phenomena.
Yes, correct.
But because of that reason, and if we think of as what's really spatiotemporal as kind of the output that is equivalent coming from each of the picture, and we should identify space-time kind of there at that picture, then one should be kind of wary of taking the specific compactification, even including the diffeomorphic structure, to kind of too straightforwardly, because the diffeomorphic structure of the compactification might be different from this manifold to this manifold, but you can still ask the kind of completely, because we know that they have to be.
Well, I think that
we know. Let me just finish.
Yes, sorry.
We know they have to be empirically equivalent. So if we can then, even though we have these completely different pictures, we can then, given fixed values of these parameters corresponding to these parameters, we can ask the question, what would that kind of empirical or phenomenal space-time look like? And in general, it doesn't have to agree with any of those pictures, right? So that's where I would like to identify. That's at the level where I would like to ask the question about space-time in terms of this kind of metrical space-time, empirical space-time we see. And the other ones, they are also kind of mathematical underpinnings in some sense.
so. Okay, I see your point. Although I'm not sure I agree when you say that the differentiable, they are not diffeomorphic. So okay, no, that's.
Well, if two non-topologically equivalent can't be diffeomorphic. Right?
I'm sorry, say it again.
So if you have, if the topologies are different, they can't be diffeomorphic, right? So
Yeah, but the way in which you are smoothing, deforming, I mean, the constraint here is that it works if you are building a differentiable structure on the moduli space, which arise from the fact that you are deforming by using a C infinite smooth function of deformation. So if as long as this is well, as long as they are diffeomorphic but metrically inequivalent, then you have the insensitivity of the observable, of the physical observable of the system when it moves from one fiber to the other by
but now
using.
you're still talking just within one moduli space, where the question of duality,
Yeah,
you
but
have
the idea.
two one that you then can,
Yeah, but I mean, you don't really need to have two ones. I mean, you can. I mean.
But to address the question of duality, I mean,
That's
then
true.
You need to ask those questions, right?
Yeah, but you know, you now feel this need to take in consideration two moduli space. But what I was doing here was looking to the local infinitesimal structure around one fiber into the moduli space, and to see that at least as long as I preserve diffeomorphic invariance, I can claim a thesis of metric background independence. So what I'm doing is thinking to the local first order infinitesimal open set around fibers, and that shows you might be looking for an even stronger theory of background independence in which you are appealing to global properties of the moduli space, but that's not really something which is a kind of step which would be straightforwardly implied by what I'm doing, because what I'm doing, and I emphasize this by using the word look, I'm taking C infinite infinitesimal deformation around the parameter, because I skipped a lot of slides actually. And why is that? Because at least in
Because I kept telling you to hurry up.
because he told me to hurry up, and so now nobody understood what I was doing. But I'm joking. But I think for now I feel more comfortable to look to the local infinitesimal structure and to see how much information about physical space-time and its possible deformation in a
but the point
represent the sort of causal connections that are happening. You know, you've got overlap in the description. Topological overlap is enough to get at that. And so really the key point there is that it's sufficient to represent some sort of causal relationship between what's happening in the mechanism. But that seems to suggest that once you've moved to the setting where you're talking about topological information that seems to be relating space-times rather than within a space-time, that you've lost what it was you were calling mechanical, namely the causal relationships between bits, processes, events of the mechanism.
Okay, so yeah, and as I said, the huge challenge is that mechanical explanation requires that things are in space and time to be somehow mechanically explained. I mean, right? Yes, you are absolutely right. My way of trying to say, look, this notion of emergence, a way of proposing a mechanical explanation is around. I mean, develops around the idea that well, look, if there is no way to if the idea that there is a fundamental metric in the background of dynamics doesn't really have any explanatory role in why a certain manifest word is used. What does it mean to assume or to posit that the fundamental geometry, whether it is there or it is not there, it really doesn't have any causal power, and so if I cannot collocate space and time into the set of features, of fixed feature of the background of what David calls arena in his book, somehow prior to the mechanical feature of the world. And what do I mean with mechanical feature of the world? Well, what everyone means, right? Distribution of matter and the dynamical laws that distribution of matter, distribution of material bodies and the dynamical laws they obey, right? So if I cannot put space and time into the set of fundamental feature of the background, somehow to the mechanical feature of the world, because whether or not they are there, they don't play any causal role, then, and this is a problem of underdetermination delivered by Poincaré a long time ago, then I can infer that probably the reason is because they are mechanical feature. They are not prior to the dynamical feature of the world. I know that this is a kind of very not straightforward way of thinking. I mean, it's a kind of problematic way of extending the traditional notion of mechanicism. So the huge challenge here is trying to remain a mechanicistic philosopher, as I was to do for all my life, but try to look to what's going on in string theory or in quantum gravity by trying to preserve as much as I can of this mechanicistic approach. So it's a kind of indirect strategy that I'm using by appealing to the Poincaré parable and the Poincaré argument. So I don't know if it helps, maybe not.
I mean,
but
that was the stuff that I was on board with, and then I'm worried about maybe the intersection with your use of mechanical and the usual use of mechanical is empty, in which case, why not use a different word? But
yeah.
You're thinking about the people who got, I don't know, about mechanistic explanation a few years ago, but it had very much to an example you were sort of giving.
Well, mechanistic
specific definition of mechanical.
Yeah, no.
But you don't have.
Yeah, there is a landscape of definitions of what a mechanical explanation is, and actually, I mean, Carl Caver and the other one that gives, so and actually in that paper there is a very nice presentation of all the ways in which mechanical explanation is defined, and the one I was actually thinking was the one that fits into this case. So it doesn't, you're right, I should have said probably something more specific about what kind of mechanical explanation.
That's what questions are for, I think.
Yeah, that's true.
Okay, but we need to wrap it up. Look, it's getting dark. I can even hear their stomachs rumbling over there. It's nearly 8 o'clock at night in Geneva.
They want to leave. That's a way to tell us they want to leave. Why did you switch off the light?
No, because it was light to start with. It's just been getting dark during your talk.
Okay. Do they yet? They don't have electricity.
They don't have electricity in Switzerland? No, they have electricity.
They can't find.
All right, but let's bid them bon nuit, I guess, and
Bon nuit.
say goodbye. Thanks, and thanks for say thanks to
Thank you.
Tiziana again.